Okay, well, thank you for the questions. I have worked out the number of wind turbines, but we can come to that afterwards. So the second session, I'm going to cover renewable electricity technologies and then dive more specifically into onshore wind. Now, the first bit of the renewable energy technology session is to give some comparisons, and then we'll talk about deployment of the various technologies in question in Devon, which should answer some of the questions that you were asking a little while ago. So just to talk qualitatively about potential renewable electricity generation technologies, I put together this sort of short table. In terms of electricity only generation technologies, we've got onshore wind. Now, onshore wind is the largest unconstrained renewable energy resource, just simply because the amount of wind that blows across this part of the country. But in practice, it's highly constrained, and I'll come to that later. Photovoltaic, the Southwest has the best photovoltaic PV resource in the UK, and ground-mounted PV is the largest resource once we've applied constraints, we find. The other renewable electricity resource that's often talked about, but is very difficult and not very big, is run-of-river hydro. It's small scale, the resource is small. Abstraction licenses, which means the amount of water that you could take from a river are restrictive, because clearly you can't take all the water to generate electricity. And the economics of run-of-river hydro are really difficult unless you've got existing civil infrastructure, civil engineering infrastructure in place. So a mill leat, for example, that already exists. But really, the scale of it is small. The other technologies...
Tony, before you go on, can I just check? Photovoltaic, that is solar essentially, isn't it?
Absolutely, sorry, yes, solar photovoltaic, yeah.
Okay.
Yeah.
Thanks.
Yeah. Moving on to technologies that produce both heat and electricity potentially, we've got biomass and anaerobic digestion. Now, in these instances, the resource isn't directly linked to the location of the technology, because clearly when it comes to biomass, it can be harvested in one place and moved to another. And the same is true with anaerobic digestion, which is a process that our food waste undergoes in some instances to generate biogas. Now, to maximize the efficiency of both those when they're used for heat, we need to have a heat load as well as electricity there, which makes location very site specific. And the preferred solution for anaerobic digestion is really to clean up the biogas and put it into the gas grid currently. So there are challenges with electricity and heat production. Now, when we look at the cost comparisons, now this doesn't cover all the technologies, but it covers the cost competitive ones. These are statistics from Bayes, and it shows that onshore wind and large scale solar are the most competitive cost renewables. And when you compare it with gas fired generation, so combined cycle gas turbines, the bar on the left, the current costs are actually cheaper than gas, even when you don't include the cost of carbon, which is the dark blue bar on the left-hand bar of this chart. So onshore wind and large-scale solar are very cost competitive. I think it's also interesting on this chart to point out that there's a pre-development cost where money is at risk for the developers of these technologies. And when we look at onshore wind, the development cost is about 1/15 of the full cost, if you like. Now, that gives us a feel for the sorts of risk and reward ratios that developers going into a wind development might think about. So if they think that the development costs, when they risk weight it, outweighs the benefits that they might get, then they're perhaps unlikely to pursue a development. So the sort of risk about whether my wind farm's going to happen, is it less than 1 in 15 chance, or is it more, for example? And that's a question that developers are going to be asking themselves. And if wind development for example, is very, very difficult, they might be thinking that actually the risk is probably more than that. So these are questions that have to be overcome when we talk about wind development at the outset. So what has been the outcome in Devon? Because perhaps the best way to think about what is good is what the market's decided to put in place. And this is what's happened. This is where we're at in 2018 with renewable energy, with renewable electricity, I should say, in Devon. So PV at 550 gigawatt hours is the most dominant technology at the moment. Wind is around half that, at about 270. And as you can see, the other technologies are sort of also RANs. Even added all together, they come to less than onshore wind. And technologies like landfill gas is something that's going to decline over the years. So that bar will shrink rather than grow. So you can see that the market as it is says photovoltaics and onshore wind are the most interesting renewable electricity resources to be developed. The next slide compares the current renewable energy generation in Devon with what we currently use and what the constrained resource, the currently constrained renewable energy resource, is estimated at. So here's the total 2018 renewable energy production on the left, split down into the various segments, compared to our 2018 electricity consumption. So at the moment, about 22% of Devon's electricity is produced in Devon. Of course, that's much less than the UK's overall renewable electricity consumption, production as a percentage of consumption. And you can see there the resource in Devon, which really significantly, the potential resource, constrained resource, I should say, as well, significantly exceeds our current electricity production. And where by 2050 our electricity production to double, we can see that the total constrained renewable energy resource would actually potentially meet that as well.
Sorry, Tony, I'm going to cut in again. Just with just a clarification on the sort of constrained renewable electricity resource. What's the constraint mean?
Well, I suppose I'm going to answer that in the last part of my presentation, when we come to look at mapping, how we map renewable energy and how we decide what sort of capacity the county has for holding renewable energy development.
Great,
so
thank
I'll
you.
come to that. Yeah. The last slide in this section is about how renewable energy capacity, not just wind, has developed in Devon over recent years. So these again are base statistics, and it shows that we've seen a really significant rise between 2014 and 15 in particular in PV development, and then that's tailed off but still continued. When we look at wind, well, there was some development between 15 and 16, but since then it's really flatlined. And the other technologies sort of flatline along the bottom as well. So yeah, not as really an exciting picture recently for the development of renewables in Devon as a whole. Now there's a number of reasons for that, but we're focusing on wind. And that's what I'm going to do in the next part of the presentation. So the key points really from those slides on renewable electricity technologies as a whole is that solar and onshore wind are particularly cost-effective renewable energy technologies. But pre-development costs are at risk. And when developers look at developing renewables, they will think about what the pre-development costs are that they've got to bear without having any revenue from their investment, compared to the risk of actually getting that revenue. 80% of Devon's current renewable electricity is solar and wind, and renewables produced about 22% of Devon's electricity in 2018, of which 6% was wind. Devon's constrained renewable electricity resource exceeds substantially 2018 use. In fact, it could withstand potentially a doubling of electricity use. And after solar, wind is the largest constrained resource that Devon has, given the current constraints. But wind development in Devon has flatlined since 2016. It's essentially come to a halt. So I can now move on to the last section, where I'm going to dive into onshore wind in Devon in particular, but in Devon in more detail. And the first couple of slides are, and my apologies upfront, horrible. They're graphs taken from academic papers. And the first one in particular, I'm not going to try and explain in full. I'm just going to try and produce one point from it. So apologies for this, but here it comes. Now, the only point I want to make from this slide is that it compares a range of technologies. And the point I want to make is that wind has the lowest embedded energy use as a percent of its lifetime production of all the technologies here, at about 3%. Now, this is a model, it's not actual data, and it's a worldwide approach, not necessarily a European one. The next slide looks at actual data from European wind turbines, and I'd like to keep hold of that 3% number as percentage of lifetime production as we go to the next slide. So this graph shows turbine power across the bottom, going up from left to right, versus the carbon payback in days on the left, and the percentage of lifetime on the right. And you can see 3% tracks across to about 220 days carbon payback. And what this graph shows is that you can achieve that payback with a relatively small turbine. As turbine sizes increase and you move along the dotted lines to the right, so say a 3 megawatt turbine, we're talking about 75-day payback for the embodied energy in a 3 megawatt wind turbine. That's very low. And I sort of go back to the point I made in answer to one of the questions, that we didn't really ask this question about our fossil fuel investments and our fossil fuel systems, but the question is asked about wind turbines, and the answer is quite clear. The carbon payback is very quick. So let's drill into wind turbine development in Devon. I showed a general graph showing that it had flatlined recently. This is it in more detail. So this is from the UK Wind Energy Database, and it shows the number of projects, the capacity of wind turbines in Devon that have developed between 2011 and 2018. So in total, we've seen 41 projects building 89 turbines and developing capacity of 142 megawatts. And you can see the cumulative orange one, but the annual one in blue. And so the first big ramp there is one of the 3 larger projects. And these 3 large projects have put up 40 turbines and 102 megawatts. So you can see the large projects have made a big contribution to the total. And the largest of them was Fullbrook Down in North Devon, which is 22 turbines at 66 megawatts. And as I pointed out in my first slide, that would supply about 80% of the homes in Exeter with electricity, if they use the average amount of electricity used in a UK home. The other 2 projects came in 2016, and that was Denbrook, which is just north of Dartmoor, and Batsworthy Cross, which is again in North Devon. And I'd just like, as a case study, to go through what happened at Denbrook, at the wind farm development there around North Taunton, just north of Dartmoor. And I've put a sort of timeline on the next slide to show that process. Now, it came online in 2016, but the application for Denbrook was made in 2004. So it took 12 years to get from initial proposal to starting operation. The initial proposal came in 2004, planning application was submitted in 2005. West Devon District Council then refused planning permission. The developer appealed to the planning inspectorate and requested a public inquiry, and that public inquiry was held. Planning consent was granted by the inspector in 2007, but objectors took that to judicial review. The judicial review didn't overturn the consent, but the objectors then took their case to the Court of Appeal, and the consent was overturned on a technicality. There was then a second public inquiry, and consent was granted with conditions. That was followed by a second judicial appeal by the objectors, which didn't overturn the consent, and a case taken to the Court of Appeal in 2011, which was dismissed. Construction began in 2015, and the wind farm became operational in 2016. Now think about the upfront cost that the developer has put into this application and the likelihood of getting that application through to deliver revenues to repay those upfront investment costs. And I was talking about a risk maybe of 1 in 15, something like that. I suppose it would be interesting to look at the number of applications there have been and the number of successful and unsuccessful ones that have been for wind applications across Devon. That's not data I have, but it would be interesting data nonetheless. So that's a little case study of a wind farm development. And although wind farms develop a flat line since 2016, you can see that this process started 12 years before that to get that wind farm built. So in the questions, we had some thoughts about where the main sites for wind farms would be across Devon. Well, we've been undertaking mapping processes, and the most recent we've done for renewable energy mapping was for Teignbridge District Council as part of the evidence base for their local plan. So I'm going to now use that as a sort of second case study about where wind development is likely to happen. So there are big constraints around wind development, and these are the ones, or the biggest ones that we used in the work we did for Teignbridge. Now, these are the current constraints. Of course, these could change, but I'll show you what the constraints are, what areas of, in this instance, in this case study, Teignbridge, they take out, and then we'll see the implications for that as we look at the maps that result from it. So here are the key constraints: aircraft communications, power lines, roads and railways, of course, buildings, green space, national parks, because of course, you know, any thought of building wind turbines on Dartmouth National Park, which intrudes into Teignbridge, are currently out of the question. Local nature reserves, where there's water and lakes, woodland, and where the wind speed isn't big enough, of course, so it's a key constraint, and where there's not a relatively local grid connection point. So what we used here was 2 kilometers as a distance from the current high voltage electricity grid to screen out sites. So here are statistics on the biggest constraints. So 77% of land's taken out because it's within 400 meters of residential buildings straight away. 52% of land is taken out because it's more than 2 kilometers away from a 33 kilovolt high voltage electricity network. 38% of Teignbridge is taken out because it's in Dartmouth National Park. A similar amount taken out because it's within 150 meters of a motorway or road, or 75 meters of other roads. 23% taken out because of aircraft communications. 20% has wind speeds that are too low at 80 meters to realistically put wind turbines in. 18% by woodland is taken out. So there you can see the sort of major constraints that the largest constraints that come in. Power lines, green space and water are relatively small constraints compared to the ones I've highlighted there in red. So when we map, what are the results? Well, with all those constraints, there's not a huge number of areas that come up as potential wind sites. And you can see here the scattering of areas that we come up with across Teignbridge in this sort of case study for Devon, if you like. And what it results in is that about 1.7% of the land area of Teenage is potentially suitable for wind development. And of course, our mapping doesn't mean to say that there aren't unmappable constraints and issues that would actually mean these sites are not suitable for wind development. When we apply to try and scale what the capacity of this is, a density factor for wind turbines, so we remove 50% of lands for smaller ones and 80% for larger wind turbines, and our capacity factor, which I referred to in my first slide, really, changing capacity into production. We estimate that the resource in Teenbridge is 89 megawatts capacity and about 217 gigawatt hours. Now, Teenbridge is only a small part of Devon, but it shows you how these numbers, come down to small areas, and after you apply density factors and capacity factors, these are the sorts of numbers we end up with. And I've put there the link to the evidence base that we've produced for Teenbridge, if you want to follow that up. So that's what my last slide really. So it remains for me to summarize the key points, if you like. Oh, that's a nice addition. I'd forgotten that. Yeah, you need some perspective there. 46% of Teenbridge's current LE reduction if all that resource was developed. That's a nice statistic to have. So that's higher than, considerably higher than the 6% of Devon's energy that wind currently produces. So the key points, onshore wind turbines repay the carbon embedded very quickly, for large turbines within a couple of months. Development of wind can be difficult, as we've seen from the case study for Denbrook. Risks involved in the planning process, I would argue, has led developers to largely withdraw from wind development in Devon. Onshore wind development has stalled because of that. There are other reasons that, for example, grid constraints that have the upcountry that have made development difficult, but fundamentally, instances like Denbrook have really put wind developers off, in my view, from coming to Devon. Potential sites are very constrained when you apply the sorts of constraints that I listed. But despite those constraints, the onshore wind resource is significant. If all that resource in Teenbridge was developed, 46% of current electricity production is not bad, because you've also got the solar resource to consider as well, which of course we haven't covered here. So those are the take-home points, if you like, from the last part of the presentation.